Hello everyone, we're Team 14 of Artur, Michael, Basil, and Baha, and our senior design project focused on the design and implementation of a hydroponic greenhouse in rural Uganda. For the past 2 semesters, we've been working with Jolly Lux and her organization Guiding Light Orphans, which is a nonprofit based in Avon, Connecticut, which has a goal of strengthening child health and reducing infant mortality rates in rural Uganda. One of the main issues that GLO works to address is the malnutrition crisis currently occurring in Uganda, where over half of children under the age of 5 have anemia, a third have stunted growth, and a quarter are underweight. One of the most common avenues to remedy this is the agricultural route, yet unfortunately Uganda is plagued with difficult growing conditions, including substandard soil, low water quality, and arduous weather conditions. The solution that our group is proposing is hydroponics, an agriculturally based method and system that relies on using nutrient solutions rather than soil to grow crops. With our model in place, we believe we will be able to counter the constraints in place and provide the people of Masindi a proper balanced diet as well as a varied food supply, and overall provide a suitable and adaptable solution to their malnutrition crisis.
We used CAD software to develop a visual model for our greenhouse design. As you can see, we divided our facility into 3 main sections. The first will house all of the food crops in a nutrient film technique, or NFT system. NFT is the best type of hydroponics for this particular application, since it's cost-effective and can accommodate a large variety of nutritious, leafy green vegetables. These types of crops grow quickly and easily in hydroponic systems, making them an excellent choice to combat the hunger and malnutrition in the area. Our facility includes 8 separate NFT systems, each of which will accommodate a specific crop. Each NFT growing bed will then have up to 80 PVC growing channels, which are supplied with proper nutrients and water from a separate reservoir. As you can see here, a low-power submersible pump is sufficient to provide each plant with a constant nutrient solution flow rate of about 6 gallons per hour. The next section of the facility houses 2 1,000-gallon water tanks along with an industrial refrigeration system. The water tanks are used to refill the smaller NFT nutrient reservoirs and the fodder reservoirs. The refrigeration system will be used to store harvested crops before they can be sold or distributed to members of the community. This section will also be used as a nursery for the food crops, since seeds must be germinated and plants must sprout before they can be transferred to the NFT system. Finally, this section will store all the tools, equipment, and supplies necessary for the operation of a hydroponic greenhouse. The final section of our greenhouse will be used to grow fodder for livestock in the local community. Using hydroponics to grow fodder has become a common practice, and a shelving system with trays is often used. As you can see, our design consists of 6 vertically stacked shelving units, each containing fodder at different growing stages. This ensures that there is a constant harvest and thus a constant food supply for local livestock.
Here is a simplified depiction of the water distribution in the greenhouse. Groundwater is first pumped up into the respective fodder and NFT water storage tanks, which can hold a surplus in the event of a pump or power failure. On the NFT side, water is manually pumped by operators into each of the 8 NFT system reservoirs via a hose, where it is then cycled through the system over the next 2.5 weeks. Because nutrient solutions must be tailored to plant species and varieties to maximize yield, each nutrient formulation is added separately to its respective reservoir. To compensate for water loss due to evapotranspiration, fresh water is supplied to the reservoirs daily. After a period of 2.5 weeks, the nutrients have been depleted, warranting a replacement of the total reservoir volume and a reapplication of the nutrient formulation. On the fodder side, because all the units use the same nutrient formulation, it can be added directly to the storage tank. The resulting nutrient solution is gravity fed to all of the fodder unit reservoirs using float valves, where it is then pumped up throughout the height of the volume and sprayed over the fodder trays, where it is then transpired. Water cycles occur 3 times a day and are set on a timer, thus allowing the unit reservoirs and the storage tank to be resupplied between cycles.
For the economy analysis, we divide the economy analysis into 3 categories. First of all, construction. The greenhouse will be 50 feet by 165 by 10, and the cost estimate is about $60,000. Second, power requirement. The greenhouse needs 14 kilowatt per hour to be fully run, so the average solar system cost for the 14 kilowatt per hour is $60,000. This is based on 1.6 square meter for the panel size with 20% efficiency and 6.5-hour sunlight per day. Finally, equipment and material, which include PVC pipe, pumps, PVC and cap, polytubing, water storage, nutrition solution, and more. So the estimate for the equipment and material is going to be $55,000, and if we include the construction solar system, this puts the total capital cost estimate about $175,000.